So today I'm talking about some brand new work, and that's exciting for me, and that gives me permission as a scientist to speculate about what this new work might mean. We all know, and we've been hearing from these fabulous speakers, that experiences that the prenatal period and the postnatal period have an incredible impact on the baby brain. The work that I'm going to talk about today with music is going to explore how it can work that relatively simple and routine experiences that babies can have in many, many households can make a difference to their brains quite broadly, that music might be able to affect not just the auditory system, but the cognitive system, the social system, and the linguistic system. And so we want to get to the mechanisms underlying these things. So let's see if I can convince you of all of that. The disclosure, I have no disclosures. I co-direct an Institute for Learning and Brain Sciences at the University of Washington. We've been working out how the brain of the baby gets built, and the tools that we've brought to bear in the past 10 years are very, very magical and wonderful brain imaging tools that we can use with little babies. So here you see a little baby in a very big machine. This is magnetoencephalography, and you'll see a bigger photo of this later. Basically, the baby is free to move. It's a noiseless machine. We can track the baby's head and let the baby experience something while we see a movie produced in the brain as the neurons do their work. So we've been looking at the effects of experience on brain function. We've also been doing studies that look at structures in the brain. So how is it that the areas of the brain responsible for hearing, responsible for seeing things, responsible for touch, how are they building up? And the neural connections, these wonderful superhighways that are running between areas to allow them to communicate. So these two brain function, brain structure, along with behavioral studies of the baby have taught us a tremendous amount over the last 10 years. So much so that we're now moving towards interventions that really make a difference to children and families. So the science has really come along. The science of the baby brain has come a long way since it began with the tools of modern neuroscience about 10 years ago. So what's our main question? What are we trying to answer in the experiments that I'm going to talk to you about today? The basic question is, why is it that early experience is so potent? How can it work that way? How can a simple experience that a baby has have a cascading set of effects in the brain that make a difference and allow early experiences to predict later outcomes? You've been hearing from a variety of speakers today who show you that in different domains, those early experiences matter, and the metrics we have for measuring those behaviors early predict outcomes later. It's a very valuable thing to know. So one of the things that biologists have taught us is that there are periods in time, both in animals and in humans, that we call critical periods or sensitive periods. They're periods in which the window of opportunity opens and what's coming in the environment floods the baby brain and makes a huge difference. And then that window, it doesn't shut tight, it doesn't shut completely, but it really does narrow. And so we're trying to understand, is that what's happening in development? There are these critical windows of opportunity. They're opening, experience floods in, maps huge amounts of cortical tissue and builds architecture. Is that what's having these cascading effects? So let's look at a critical period, the one I typically study. Music is new for me, but the one I typically study is language. So here's something you all know, that if you're exposed to a second language between the ages of 0 and 7, you're going to learn it a lot more, and a lot more completely than you will if you go after the age of 7. So between 7 and puberty, every 2 years, there's a small but definite decrease in your ability to learn a second language automatically. Well, within that first 7 years, there's a sensitive period that happens in the first year of life, and that's the one I've spent a lifetime studying. So in the beginning, babies, in order to learn words, babies have to know what sounds are used contrastively in the language. Japanese babies and children have to learn that R and L don't make differences between words, whereas American babies have to learn that R and L, rake and lake, read and lead, they make differences in words, so you have to know what those sounds are. Turns out that early in development, at 6 months, as this graph shows, and I demonstrated this all over the world, at 6 months of age, babies are universal citizens of the world. They can hear every distinction used in every one of the world's languages. So they're universal listeners. And then a few months later, something very dramatic happens. You can see what happens in the babies tested at 6 months and 12 months. The red line shows our American babies in Seattle listening in a behavioral or a brain test to the difference between they hear rah, 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 then they hear la. When they hear la, they're supposed to interact, they're supposed to look at something. They're supposed to do something that tells us that they heard that difference, and they do reliably. At 6 months, the Japanese babies are just as good. All babies, no matter what country they're growing up in and what language we test them with, demonstrate this phenomenon, universal perception. And then by 12 months of age, if you're listening to the sounds of a particular language, the baby gets better at those sounds. And if you're not, as in Japan, not hearing the RL distinction, you decline. So this 2-month period between 8 and 10 months is a sort of magical time for the baby brain. Something very important is happening. And of course, we've done lots and lots of experiments to understand what's happening in that blue period. And the two main things that are happening is, one, babies are computational geniuses. They listen to even though they don't understand words, they're sensitive to the frequency with which a certain sound occurs. That's also true for sights. It's also true for touch. Babies are sensitive to their experience in terms of its frequency. The more it happens, the more it makes an impression on the baby brain. So we have a statistical computational thing going on. But the more powerful result that we found to be true during this period, this blue period, is that the social brain controls when babies take statistics. So unless it comes from a human being, babies aren't taking statistics. We proved that by exposing babies to Mandarin Chinese for the first time in that period between 10 and 11 months. And we demonstrated that only when babies were exposed to a live tutor, a live speaker of Mandarin, did they learn. When they were exposed over a television set, or when they heard it just through an audio, an audio channel, they learned nothing. They were in fact comparable to babies who were in the control group and had 12 sessions of just English. And so all those 4 groups, the live, the TV exposed, the auditory exposed, and the babies in the control group were tested after their experiences, and only the group exposed live had shown learning. And in fact, they were such good learners, they were completely statistically equivalent to the babies in Taiwan who'd been listening to Mandarin for, by that time, 10.5 months. So, experience of the right kind at the right time has an amazing effect on the baby brain, and that's how critical periods behave. So at that time, so we've been doing this over a number of years, I had a doctoral student who happened to be a concert pianist, Christina Zhao, very, very, very smart woman. And she said to me, what would happen if we exposed babies to music socially during that period? If we brought them in for the same 12 sessions and were there with their parents and other kids, and kids love these sessions, what happens if they listen to music and interact with it? What effect would it have on the brain? Would it affect just their musical acumen, or would it affect something more generally? Now, as a concert pianist, she'd been looking at all the studies that say, if you're exposed to music between the ages of 0 and 7, that's if you've had lessons, if you've done it in a concerted way, you have skills as an adult that you don't have if you're a non-musician. But as she told me, those studies are flawed because we don't know whether there are genetic differences between musicians and non-musicians. There's never been a randomized control experiment. And so she said, I'm going to do the first one. And she did. Her goal was to expose babies to 12 sessions in a randomized control trial in which half of the babies were randomly assigned to the musical group and half of the babies were in the control group. So I'll show you the movie in a minute, but just let me explain. Babies in the music intervention group did things with their hands to keep time with the rhythm. So babies experienced waltzes, everything from Blue Danube to Take Me Out to the Ball Game, that represent that triple rhythm, that triple meter. It's a difficult meter for young children to master, so we thought this would be a perfect one for them to hear. So they were tapping it out with drums or with their feet or with their hands. They're watching the other babies. They're enjoying the social nature of it. And kids in the control group also did motor things. They had toys to play with and things to hammer their drums and things with, social with their parents, exactly the same, except no music. So let's look at the movie. Can you play that movie?
Me out to the ball game. Take me out to the crowd.
Okay, all right. So they enjoyed their little music session. So when they got done with the 12 sessions, the kids in the music group and the control group came back, and we put these little ones into our big machine. This is what a magnetoencephalography machine looks like, $2.5 million, a magical toy for neuroscientists because it's completely safe and non-invasive and noiseless. And babies, since we've invented the head tracking gear, we can put little pellets on their head so they can move. They're perfectly comfortable moving, and they can take toys from you or interact with you. They can listen, they can watch. There are many things that you can learn. So we were the first in the world to put a little one in the MEG machine, and this little one is listening over insert earphones to the sounds of many languages. And so we're able to see the firing, the magnetic fields that are picked up by MEG represent neural firing very directly. So what we wanted to do was, after these kids had been through their groups, either control or experimental, we wanted to give them an opportunity to listen to the rhythm of waltzes that they had not heard yet in their exposure sessions, but occasionally mistime the note. So the triple meter is supposed to go bump, 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 bump. But if you mistime that last note, those of you who know the waltz and expect the waltz, your brain would react to that change. And then we also gave them a speech test. We gave them a word in Japanese in which a rhythm contrast, a rhythm is defined by that word, and then we violated that rhythm after the baby said, listen to it a little bit, then we violated it. So the question is, are the kids in the music group better, and then are they better just at music or more than that, and what's actually happening in their brain? So let's look at this slide. You're going to see, it's complicated, but I'll walk you through it. We saw changes in two parts of the brain. Here's the sensory motor, this is auditory cortex, and what you're seeing in dark blue is the babies in the music group and the green in the control group, exactly 200 milliseconds after the missed time. And you can see this huge effect plotted over here, highly significant, showing that in that auditory area, the babies were better at music. Now, this is what we expected. This was the prediction. But here was the first surprise. The surprise is that we were also affecting prefrontal cortex, where attention and executive function and all those sort of higher level cognitive things go on. And here again, you see at exactly that time that there's a difference between the experimental group, the music kids, and the kids who didn't experience music. Again, highly significant. So that became very, very interesting. We didn't, an experience comes through a sensory modality. We didn't just change that sensory modality, we changed prefrontal cortex. We trained the baby, we thought, to attend to that pattern. They were looking for that pattern, expecting that pattern. So if you start thinking that something broader is going on, then the speech condition gets interesting. If the babies have been trained about patterns generally, then maybe you should see an effect on speech. And indeed, that's what we saw. So here again, we're looking in auditory cortex, and you see the effect. Now this one is, we go exactly 200 milliseconds after the rhythm change occurs, and again we see a big difference between the blue and the green, and similarly in prefrontal cortex we see a significant difference between the kids in the music group and the kids in the non-music group, and here are the plotted data. Okay, so we've seen a fairly simple experience, only 12 sessions, it's only about 5 hours of experience, have a pretty profound effect, not only on that sensory system, but on the systems that pay attention to patterns. And our interpretation is that we have trained these babies, this experience has trained the babies to pay attention to patterns. That patterned experience is what the world is about. That as you exist in the world, the idea is that predicting what's going to happen next turns out to be very important. It's very important for finding salient events. It's very important to social interaction. It's very important to cognition, to predictively code the experience now so you know what's going to happen next. So we think that what music can do, and maybe a variety of experiences can do to the baby brain, is to affect them in a more profound way than you might imagine. So visual patterns, auditory patterns, haptic patterns, they may come in and change sensory systems, but do a bigger job than that. And we believe that there are very big implications of this. So you heard both Andy and you heard a variety of speakers tell you about the role of synchrony and about music in particular, that music may have an effect on kids' social performances. So Andy had said that musical experience helped children, especially when they were synchronized in their movements, were helping children be more cooperative. We did not take a social measure, but we did take measures for the students who were testing the babies in the MEG, who did not know which group they were assigned to. They were rating the kids on the basis of how calm or agitated they were. And after we looked at all of the data, the babies who had been in the music group were significantly calmer. It had produced a kind of calm behavior in the infants in the group, a kind of social effect that we plan to study further. It definitely has this cognitive effect of making a difference to prefrontal cortex. And in studies that we're doing now, we can see that the babies who have been through the music experience have greater abilities to attend, to hold attention when that's important, and to switch attention when it's appropriate to switch. In other words, we think that music is affecting executive function. And then finally, we see that this effect of music is operating on babies in what we thought was a critical period for speech. And so it raises very fundamental questions about sensitive periods, at least this particular one, to saying, what's it a sensitive period for? Is it a sensitive period for all of complex auditory signals? Is it a sensitive period for patterns? And would visual patterns do the same? So it has those basic questions, but it also affects what we think about practical, our knowledge about the routines that we've been thinking about with regard to parent-infant interaction. Again, many speakers emphasize the daily routines of parents and how they interact with kids. Even simple things like peekaboo, the idea that babies live for the expectancy. It's very fun to predict the future. It's very fun to know that you're engaged in something where the next thing that's going to happen, you know, you're delighted about it. In fact, I think kids seek out those predictable patterns because it makes the world less chaotic. So for a moment, think about the kids who are being reared in a chaotic environment, a toxic stress environment. Where are the predictable patterns? Where is the delight in understanding what's coming next, of seeking those routines and expectancies that bring not only delight from an emotional standpoint, but a cognitive boost? And I think that what we'd all agree is that a chaotic world and toxic stress would not produce the kinds of things that simple routine experiments do. So at the moment, we're engaged in tests in which we examine whether or not music could modulate stress. We're not only doing that in Seattle with babies, but we're beginning to plan some collaborative work with Jack Shonkoff's center at Harvard, and where we're using a mouse model. Mice, too, are very sensitive to auditory experiences. There are sensitive periods, and it's possible that we can modulate the effects of stress with experiences like music. So the bottom line here, whoops, went too far. The bottom line is that we demonstrated that early music experience, it does enhance their ability to detect and extract patterns, not just for the ones they heard, but things more broadly. and that the effects go beyond sensory systems to affect cognitive systems, complex pattern recognition, and that would promote success at a variety of cognitive tasks. So we're pursuing this as a postulate about what these studies show, and I love the result that art and science may yet be unified at a time in which our schools are subtracting art and music and things that have to do with play and exploration and synchronous activity among kids and with kids and adults. So I think these small, relatively small designed experiments can have very, very potent effects on our understanding, definitely on children's brains, and that will be good for all of us. So thank you very much.